Welcome and hello. This is a video tutorial in HEC RAS, and in this lesson, I'm going to be talking about stable channel design. This is one of the hydraulic tools available to us in HEC RAS, and it's located up here in the Run Hydraulic Design Functions. And then what we're going to do is click on the Type menu and select Stable Channel Design if you don't already have it checked. So click that, and then boom, comes our Stable Channel Design calculator. The stable channel design function will allow the user to easily compute the hydraulic parameters of a given cross-section, use that information to design a stable channel with regard to its size and armoring, and then determine the sediment transport capacity of that cross-section. So again, what we have here on the screen is the interface that we're going to be discussing in this lesson. I will leave a link to this webpage from the HEC RAS User's Manual in the video description if you're interested in reading all the details. So let's go back to HEC RAS here. Just taking a quick step back, what I've already built here, you can see in the geometry data editor screen is a single river reach with a cross section every 500 feet from 5,000 down to 0. I've also already ran a steady flow simulation here with profiles ranging from 1,000 CFS up to 10,000 CFS. And I have my results computed. As you can see here, 1,000 is this bottom water surface elevation and 10,000 is the top. All right, so let's go ahead and use that calculator. I'm going to go again, run hydraulic design functions. Make sure the type is stable channel design, and it is for me. And right when you open this up, you may be prompted to specify a new sediment reach. I just typed in SCD1 for my title here. And then here is the HD file path over to the right. Over to the right here, there's 4 buttons that we've seen in some of these hydraulic calculators, such as default, apply, compute, and report. Now, I've already gone ahead and entered some data. If you don't have all your data entered, you're not going to be able to click compute. It'll be disabled until all the required data is filled out. Defaults will reset the default data. Apply is basically the same thing as saving your data. Compute here will initiate the execution of this calculator, and then report will provide a report output of the results of the computation. As you see here, there's 3 tabs, and each of these tabs represents a different method to calculate stable channel design. We have Copeland, regime, and tractive force. Each method uses different principles to determine channel dimensions that maintain equilibrium between sediment transport and deposition. I'm going to go back to the user's manual just to show you the final outcome of what we expect to see here. So this is for a Copeland method. What we get is an output table that shows the bottom width or depth of water versus the energy slope here. So this is the first 3 columns that we're looking at. The bottom width or the depth is going to be the independent variable on the horizontal axis, and the energy slope here is going to be the vertical axis, and that's in this plot right here. So we're going to see a plot like this where we have the aggregation and the degradation, and then this blue line is sort of the threshold or the terminator line between the two. In this case, we're using base width. So as the base width increases, then the threshold between aggregation and degradation also changes with the slope. So the slope here is also increasing on a linear scale. Aggregation here, this refers to the long-term accumulation of sediment that causes rising riverbeds, and that is associated with excess sediment in supply and low flow rates. And then the opposite is true for degradation. This is the long-term erosion of sediment, which lowers riverbeds, and that is typical of inflow that is lacking sediment in supply and also higher flow rates. So typically, the higher the slope, the higher the flow rate, and more likely you're going to have degradation. And then the opposite is true. Lower flow slope, lower flow rates, more likely going to have aggregation. Again, this specific plot right here is based on the input data, which happens to have a flow rate of 3680 CFS, and then the total sediment concentration is 17.47 parts per million. Okay, this is a different example though than we're doing. So let's go ahead and fill out the data, do our own example, and then talk about all the inputs and outputs with a little more detail. All right, so with this first tab here on the left, Copeland, we'll talk about that first. I have that selected. The required input right here is the discharge. So again, when you're starting this up, it's going to be blank fields. I believe the specific gravity of 2.65 is entered, but most of these fields are blank. So I went ahead and just typed in 1000 CFS for the discharge. This is the channel forming discharge. And because I'm using English units, this is in CFS. If you're using metric, it would be in cubic meters per second. All right, the temperature here is 55 degrees. That's something you can type in and override the default, but your default is going to be 55 degrees Fahrenheit or 10 degrees Celsius. And then below that, we have some optional input. This valley slope here, I just put in at 1.2%. The channel slope is 1%, but the valley slope is probably going to be a little bit steeper than that. This is the straight line slope of the land surface along the general direction of the river valley, ignoring any meanders or bends in the channel. It is the steepest slope the river channel could have if it flowed perfectly straight line from the upstream point to the downstreammost point. And then the median channel width right here, this is the representative width of the channel. Now, for me, it's 50 feet, so I'm just going to type 50 feet, but it could be more or less. And then the default regime right here, by default, this is set to lower regime. If the computed solution is in the transitional regime, then the default regime, which is lower in this case, is the one that will be used. Below that, I have some bank input data to provide, such as the side slope. So I put a 3-to-1 side slope, meaning for every one vertical rise of the side slope, I'm going to have 3 horizontal units of length. And that's true for both the left and the right bank. And then below that, I need to specify the equation to use. And my options here are either Manning's or Strickler. So I'm choosing Manning's for both the left and right bank. And then for the n value, if you're using Manning's here, you'll put an n value. If you go with Strickler, then you go ahead and specify the k value that's associated with that equation. Okay, lastly, what we need to do is specify the inflow sediment. So I'll go ahead and click this button. It'll open up a new dialog box. It'll allow me to either enter the inflow sediment concentration in parts per million, or let HEC RAS calculate that concentration based on these values right here. So what we need to do is determine a supply reach and then give HEC RAS the width, height, and slope of that supply reach. And then just as before, we have the bank input. This is associated with the supply reach with side slope. Equation is either Manning's or Strickler, and then n value for Manning's or k value for Strickler. Okay. To keep things simple, I'm just going to go ahead and use parts per million. 20 may be a little bit low as far as sediment goes, but I'll just go with that and then click OK. Once all the data is filled out here, the compute button over to the side, it should be clickable and enabled. I'm going to go ahead and click apply first just to save my numbers, and then I'll click compute. And then boom, just like that, we have a table of results that pops up. And what we see here on the far left column is the bottom width, and that increases from 5 feet all the way up to 100 feet. So there's going to be 20 rows of data in this table. And then the depth here, that also has 20 different records associated with the bottom width and the channel geometry. The third column here, this is going to represent the value on the vertical axis. That is the energy slope. And as you notice, it starts off going down rather quickly from 448 to 328 to 280 to 253. And then it finally levels out down right here where it goes 211. So we know that the minimum in that curve is going to be right around a bottom width of 55 feet or a depth of 6.46. And we don't have to do that calculation. That's what this bottom row of the table is. This is sort of like the optimal value. And that is at a bottom width of 56.37 feet or a depth of 6.38 feet. So this row right here would fit in right around the minimum, which is right around here. This table also shows a number of other data, such as the composite end value, hydraulic radius, velocity, fluid number, shear stress, and then the bed regime. So keep that in mind. We have the bottom width that increases, and then this energy slope curve. Because I'm going to just click OK here, and then click on the stability curve 1 button down here at the bottom. And then this is the data that is plotted out. I'm going to go ahead and just expand that. We have the base width here that extends from 0 to 100 feet. And then the slope, again, bottoms out at about 0.00021. That's the minimum value here. And then you see the curve here, which we just saw the numbers for just a moment ago. So we have the degradation area of the plot up here, and then we have the aggradation down here. Again, this is just for my particular model I've set up with the input data, such as 1,000 CFS and a concentration of 20 parts per million. I can go ahead and change some of that data. So say, for instance, we had more sediment, maybe 200 parts per million, and then I click compute. So we have a different bottom width here of 48.79. And then we have the energy slope. It looks like it's 0.0079. So, okay. If I open up the stability curve now, we have a different plot. See, it shows, bottoms out at 0.00079 instead of what was it before, 0.00021. So I'll go ahead and close that plot. Stability curve 2 doesn't use the base width, but rather uses the depth of water. And then again, the vertical axis is the slope. So it's a similar plot, but just sort of a different way of thinking about it when using the depth instead of the base width. Copy to geometry is this last button. If you can read it, copies the selected files to the geometry file. So if I wanted one of these cross sections to assume this new value here, this cross section we're seeing on the screen, then I can go ahead and click copy to geometry, specify the river station. And if it's a new river station, it's fine. If it's an existing river station, I believe you have to confirm that you want to make that change. I'm not going to do that right now because I want my cross sections to be the same. What we're seeing here in this side display is the particular option that we selected from the stability curve from the table. So if I open up the table, what I'm seeing is a radio button along this far left side. So what's displaying in this plot right here is the width of 5 feet. So if I wanted to maybe make that wider to like say 30 feet, click that radio button next to the 30-foot base width row of the table, click OK, and then the image updates to now show a base width of 30 feet. So this is stationed centered at 0. So we have 15 and 15. And to get the 4 points that make up this cross section here, you can check out the table down on the left. So we have the 2 points that make up the 30-foot width right here at lines 2 and 3. Station is negative 15, 0, and then negative 15, 0, because the elevation is just considered to be 0 by default. And then the depth of water would be 6.02. And then the station is going to be negative 33.05 and 33.05 for what, 66.1 total feet across. And then we have the calculated end value here for the base, and then the specified end value that we put in right here for 0.03. And then if we wanted to click the report button, that gives us the same data, but just written out in a table format. So we can do that. Print, copy to clipboard, or save as a file. All right. So that was it for the Copeland method. The other two methods are similar. They have the similar input, but maybe a little bit less output. Let's go ahead and talk about those. Next is the regime method. This method is an empirical method used for long-term stability of canals, irrigation channels, and for river restoration pursuits. Once we've gone ahead and made that selection, we would fill out this data here. So we have discharge. Again, this is the channel forming discharge. We have the D50 size. This is the grain size that we're working with. So the 50% finer would be this size here in millimeters. Then we have the sediment concentration. This is in parts per million. So again, we could use 20, 200, 100. After that, we have the temperature. This is in Fahrenheit, or it would be in Celsius if you're using the metric units. And then the side factor, F sub S. This is a little bit different. We hadn't seen this in the Copeland method. Some typical values would be 0.1 for friable banks, 0.20 for silty or clay or loam banks, and then 0.3 is more typical to tough clay banks. Once these fields are all filled in, the compute button should be enabled. So if I click compute, we have the data right here. And it looks like we don't have any side slope, but we do have equations for a single point, which represents the regime depth, the regime width, and then the regime slope. Now, this is just one point on a curve. We don't have a table of data. There's nothing stopping us from changing some of the input data, getting the output data, and then computing our own curves if we want. So instead of 100 CFS, I might type in 200 CFS, apply, and then compute. And you can see how the numbers changed. The depth increased, the width increased, and so on. And as before, we have the elevation of 0.32 right here. But if I made it so there's more sediment, say 500, that's quite a bit. And let's see, how would that would affect the depth? Instead of 0.32 and a 0.4% slope, click. Now the depth is a lot less, but then the slope is much higher. So there's a number of different input values that you can play around with that'll give you different values for depth, width, slope when you go ahead and click the compute button. All right, the last method is tractive force. And again, I have this all filled out because I was learning it earlier. This is a shear stress based approach common in gravel bed rivers, sand bed rivers, and engineered channels where sediment movement needs to be controlled. Again, we have discharge and temperature, nothing new there. Below that, we've got a few parameters that will have a left side slope value, bed value, and then a right side slope value. So specific gravity, that's pretty straightforward. Angle of repose. This is the steepest angle at which a sediment or soil material remains stable without sliding due to gravity. And then a value here between 20 degrees and 40 degrees, I believe is typical, but it depends on the material itself. I put 35 degrees. After that, we have the side slope. So I said this is a 4-to-1 side slope. So for every 1 unit vertical, you specify the number of units horizontal to define that side slope, both on the left and right side. And then, as before, we've seen this equation is either Manning's equation or Strickler, and then specify the n value or the k value. Below that, it's asking us to solve for these values down here. And what we need to do is first set the method to either lane, shields, or user-defined mobility. So let's just start with lane, for instance. If I want to specify the D75 grain size as being 1.5 millimeters and the depth to be 3 feet, then let me just take these values out. It's going to calculate the width and the slope. So double click to embolden / embolden field. Double click. Okay, so I believe once it computes, the computed values will appear in these text boxes, but they'll be bold. So let's go ahead and just give that a try. Click apply to save and then compute. And then yes, so the values came through. We have a width of 23 feet, 23.77 feet, and then a slope of 0.000131. So this is not very deep, but it's rather wide. Let me go ahead and just change this depth to something larger, like 4 feet. So we'd expect a smaller width, and I have no idea what to expect on the slope, but I'll just go ahead and click apply and then compute. Okay, yes. So as expected, the width is definitely less than it was. Let's do it one more time. Let's change the depth to 5 feet. The width will be less than 13 is my guess, and it's down to 6.74. And as you probably noticed, the table down below here is also filling out. So 6.74 divided by 2 is our 3.37 because the base width is centered on station 0. And then over to the right here, we have the diagram that shows basically the depth, the width, and that side slope of 4-to-1 that we specified. You can go ahead and do the same thing with different variables and also different methods, but I'll go ahead and leave all that tinkering up to you when messing around with this tool in HEC RAS, which is the stable channel design, which is accessible under the run menu, hydraulic design functions, type stable channel design.